Alright everyone, welcome back to my channel. So today we're gonna do a problem called the maze 2. So this is the upgrade level of maze 1, and if you haven't do the maze 1, I highly recommend do that first. Then we move on to the maze 2, but since this is just a quick upgrade. So on the maze 1, everything look the same except that the maze one is just return true or false when you reach to the destination, right? But for this one, problem is a little bit different because we have to count the shortest path. Let's say we have to count the shortest path from the start point, which is the ball right here, to the gate. To recap for who have not watched the maze one, it's just that we have a start position right here, the balls, and our destination right here. The balls can roll four direction: top, bottom, left, and right, and then it cannot stop until it hit a wall. Which means that in regular traverse in DFS, BFS, you can just move one block right here, or you can just move one block here to this point. But for this problem, it moved all the way until it hit a wall. Let's say the wall is here, right? So it can only move until it reached this point. It cannot stop in here. So just recap like that. And in this one, we have to do the shortest path. So whenever you heard about shortest path, the first thing you have to think about is BFS. So we're gonna use BFS for this problem, and especially we're gonna use a heap. We're gonna use a heap to keep track, or to make sure that we always get smallest row count. Let's say from the ball right here, we have two directions, right? We have the ball rolling here. We want to choose the shortest one. So this one right here, I want to choose this first. So we'll handle a heap right here. We will handle that case where we want to get to this position first. We're always going to choose the smallest one first, right? So let's say we are here, right? Our ball just have one direction to go down. So right now our ball is right here, right? Ball right here. So it have to choose to the left or to the right here. So of course, since this is the heap, it's gonna choose the smallest count. But when it's reached here, the only choice have when it's reached right the corner right here, the only choice is to make it down here, right? So when the ball is down here, it's being blocked, nothing happened. So it's popped back to this point where we have to choose another path, right? So choose to go here, then the ball is right here, and then we keep doing that and we keep track of the step. Eventually the ball will make it down here and reach the destination. That is just in short. We use, first of all, we implement normal BFS kind of approach. It's just a normal BFS. Then we have to calculate the step, and then using that step to put it in the heap. So let's jump right into the coding part. Let's put it this way. Let's try to make it a little bit bigger, right? Like this. Very good. So what we're gonna do here is we're gonna do the right and the row and the column. This is just a standard way to approach any kind of graph problem that is on matrix, right? So length maze 0 right there, and then we also have the direction, right? So 0 1, I got 1 0, I got -1, I got 0 right here, and I got 0 1, -1, right? Oops. Then this is the direction. So now we only need a BFS function, right? So let's call that out. So BFS, we will take like the start and end position. Then in the end, it just return something. In this case, if we cannot reach the end, we return -1. So that is our last case. So I will have the visit set right here, standard for BFS. I will have a queue right here. Usually in regular BFS, we use the DQ, right? But in here, I'm just gonna use heap, right? To always get the smallest step count. And you will see it right away. In here, I would just say heap.q.heap push, right? queue, and I will put 0 row and column. The 0 right here is our step. Initially the step would be 0, right? Step 1 here would be 0, so I would say step, row and column, right? And you can imagine it like this. So in here the step is 0, right? So this one is came all the way down here, so the steps should be 1 and 2, right? So this one it should be 2, all right? So that is where we count the step, right? So let's get back here, because we're gonna use the step to get the smallest step count. So we put it in the front, and the heap is automatically sort by that. And then we add our current row and row and column. So we have a simple while queue right here. We have the step, row, column, which is heap queue dot heap pop the queue. Then if my row equal to the destination right here, and our column equal to the destination, we return a step, right? Also we have to get the visit. We need to add a row and column in here, meaning that we already visit that step. And now we have to do a direction count. So direction in directions, we have a new row and new column, and then also new step, which is, so usually in regular BFS, right? I'm just gonna hashtag here regular, we just do row and a new column equal to the row plus row and column plus the direction, right? Oh, direction column, right? But because this ball, it won't stop moving until it hit a wall, so we need a helper function that we take this ball, this location and the direction, and we keep moving the ball in that direction until you hit a wall, right? So let's say you're here, 1 2, oh sorry, no, not 1 2, so there's actually 0 1 2 and then 3. Oh, 3 right here is a wall, so we just return this point. So this is our new row and new column. So that's why I need the function, right? I need an extra function. I will call that function row, right? I add the row, I add the column, add the direction and the direction column, and I also need to add the step, because for every single move in my row function, I want to increment my step, right? And then if my new row, new column in visit, I just continue, and then in here heap queue dot heap push, I'm just gonna copy and paste from here. Got new step, got a new row, new column, right? Something like this. So you might ask, hey, where's my save clause, the outbounds, what if it's a wall? So what we doing that in my row function. My row function, we're taking care of that. Let's say it will stop when it's hit a wall, or it will stop when it outbounds. This function will help, so I'm gonna implement it out here. So div row, right? I have the row and column and the direction column step, right? Something like that. I have the row in here just to use these two elements to row. I have a new step, which is equal to the row and the column and the step, right? So this can row function right here, you will do the checking for me. So I just gonna pass my row plus the direction row and column plus direction column for row plus row column plus equal to direction column, and then I will move my new step, so plus equal 1. Right, and then just at the end, we'll just return these 3. So row, column, and new step, right? Something like that. Also, I need to have the can row. So the row and the column, just simple save clause. So min of row column smaller than 0 would return false if the row is row or column return false. And if the maze of row and column equal 1 is a wall, we return false, and then we return true if it's all passed. So let's run this, and then at the end in here we just simply return our BFS of start 0 and start 1. Alright, let's run this, see if it's work. Something wrong, just fix that. This one, oh, one of that's go wrong. Let's see what happened. Oh, oops. Yeah, small indentation. Let's run this. Yep, and we finish. That's pretty good. So the space complexity of this one is gonna be O of row and column, like the grid, right? Row times column, also times the max of row or column, because since the row function row is looped through max of the row or the max of the column, right? And plus this one, a little bit messy right there, plus the log of row times column. This is where you add those things into the heap, but in the end it's just like O of row times column, and the same for space, also O of row times column. And I think this should be it. Yep, and if you like a video, give it a like and a subscribe, and thank you so much. See you soon on the next video.